Okay, so I'm ready to go.
Ready. Okay, well, good afternoon everybody. It's a very great pleasure to introduce as our last but by no means least speaker, Axel, who's going to send us on our way with a talk entitled Homochirality in Spatially Extended Systems.
Thanks, Lawrence. It is indeed quite an amazing feeling to have been together with you for such an extended period of time. It feels occasionally like you were permanent members of Nordida. And so it has been regular practice seeing you here every day, every morning. And it is strange to imagine that next week will be completely empty. I wanted to talk about the expansion of homochirality in a spatially extended system. This is certainly relevant to astrobiology. It is perhaps relevant to chemistry, although normally in chemistry one really has experiments that are always well mixed. And so in order to make contact with what I'm going to talk about and experiments of laboratory measurements, one really needs to be very careful and set up chemical systems where one can actually resolve spatially separate behaviors without too much mixing as we go along. And so it will be interesting, therefore, from a chemical point of view. We have already heard about aspects of homochirality in spatially extended systems, especially from Sarah. But on the other hand, we haven't really heard much during this whole meeting about this. So most of this meeting was really always about non-spatially extended system, as if an entire chemistry happens in a single test tube. And this will certainly now be abundant. There are some papers on this, especially about this topic. We had a paper in the International Journal of Astrobiology in 2004. So as we talk about spatially extended systems, it means then that the concentrations, for example, of L monomers or D monomers will now be a function of position and time, of course. It was always a function of time, but now it will be a function of position as well. More importantly, if we talk about the enantiomeric excess, we have, of course, some freedom in defining it, but the interesting quantity to define is perhaps the globally, the one based on, that's wrong, but the one based on global averages of the L's and the D's. So we have to, it may not be enough to simply have homochirality in one space. We have to wait until the entire surface of the Earth, which is one of the systems we would be like to think about, until it has expanded over the entire surface of the Earth, of course. So there's a number of papers on this aspect, and I have collected here a few of those. This is here the one by Yukio Saito's, where he used a Monte Carlo simulation to calculate the expansion of homochirality in space. So locally he assumed a Frank model at any given space, but there were random fluctuations, as you see here in these black dots or the white dots. This comes from the constant noise that we have in the system. And as a function of time, and because of the action of diffusion, so there's interchange between neighboring sites, because of the action of diffusion, the homochirality eventually expands over the entire two-dimensional domain in this case. The main result from this work is that diffusion appears like to accelerate and thereby enhance the chiral selection. Then there was work also in the same year by Raphael and Koichi, as we have seen already. Koichi showed the bifurcation diagram for this paper, but this is in the context of crystal growth, and again you see here different handednesses. The colors are very similar, unfortunately, so if you're lucky with your eyes, you can distinguish a pink domain from a green domain. If you're colorblind, you have a hard time, or if you're just sitting too far away, you will also not see that. And he certainly also considered this chirality selection in 3 dimensions. Again, in spatially extended system, this is a much more recent result by David Hochberg, who unfortunately couldn't make it here because he got ill in the last moment. What he finds is that in a highly dilute system, the fluctuations are very large because you have not many bodies to average over, and he finds that the amount of fluctuations will be important to drive you away from a racemic state, which in his case means this quantity is 0.5 instead of 0, which we normally are thinking of. So 0 means therefore enantiomeric excess of -1, and plus means enantiomeric excess of +1. So for small noise amplitudes, he finds no chiral selection. And then there is this paper that we have already seen by or this plot, some plot like this was shown by Sarah, where we have seen that as a function of the temperature, which is the effect of additional stochastic noise on the system, which produces new monomers, if this effect becomes too large in a spatially extended system, the selection of a homochiral state goes away from 1 and becomes 0, as you could imagine. You have too much mixing up the system on too short a time, and there is a sharp transition, sharp bifurcation point here. And then this is this punctuated chirality paper, which, as Sarah already said, attracted some attention in the Nature News and Views, which is very nice to see because that emerged during the time as this program was running. And so again, this is the picture that we have seen here already. In the absence of impacts or disturbances which occur in regular intervals, the system comes to a halt. And this appeared perhaps intuitively clear to some of you, but it hasn't really been explained. And so this will be part of the purpose of my talk, to explain what actually happens in these locations here. And this is very relevant, of course, to another paper also by Marcello, where they looked at the propagation of these fronts. So these are the fronts between two different chemistries of opposite handedness. One handedness here, the other handedness here. There's a boundary layer in between. And the language that they use is to say that these fronts move under the action of two forces, one of which is the tension force. And this concept of a tension force is really a bit strange, and one should really ask what exactly is going on here, because one doesn't really have, in the regular sense, or at least I don't see anything which is reminiscent of the concept of tension forces that we have normally between a liquid and a gas phase. So, like Sarah, I will be using the Sanders model, and of course, to remind you, the Sanders model consisted of the simple rules of a game where one assumes that polymers that are isotactic can continue to polymerize, but polymers that are not isotactic, and in this case on either of the two ends have opposite handedness, then the rest of the interior of the chain can no longer polymerize. As we also discussed, there is the possibility of having a polymerization in the Sanders model on either this side here in this case. So once you have poisoned one of the ends, the idea in his model was that you can always polymerize on the other remaining end. But as we discussed during Sarah's talk, only one of these possibilities may be relevant if you're thinking of nucleotides or peptides. In both cases, they polymerize only in one direction. The resulting equations from such a game or reactions are, of course, simple polymerization reactions here in the isotactic case, which leads to a growth of the chain whose rate of change depends on the monomer concentration and the previous polymer concentration. Now, one of the consequences that I would like to highlight, and that has not been discussed either during this meeting, is the fact that if you have such a behavior, such a polymerization behavior, and if you have a constant supply of monomers all the time, if the monomers don't die out, then there's an interesting time-dependent behavior of this system, which has nothing to do with spatial extent. It's just a polymerization model, which I'm not aware that this has been actually tested in or seen in any models, but it is perhaps possible. So what is shown here is basically in chromatogram, where we see as a function of the length of the chains the abundance at different times. Here's an early time, here's a later time. And to see this as a function of time, I've inserted here a little such plot. You see, as the experiment starts, one sees gradually the buildup of longer and longer chains, as you would also expect. People familiar with a similar equation recognize that this is really a wave equation. So one of the ways how one may envisage seeing such behavior is by doing chromatography, but stopping the samples at regular time intervals. So I would wonder whether that's something which is practical. But this would allow us, of course, to determine the rate coefficients and their dependence on the chain length. So another aspect of this model is that if we do have enantiomeric cross inhibition, which means if there is some spoiling of the polymerization process, a racemic solution can emerge. And the racemic means that both handednesses are equally possible, and it also implies typically that the chains are very short. Here's again shown the chain length and the probability of abundance of finding chains of given length. The longer the chain, the smaller is the concentration, as we know. But if the system is away from equilibrium, such a state is not stable, and we can look for the stability of such a system. And again, we start with the solution here, which we now perturb slightly, so there's two different colors superimposed on each other. And as the system continues, these two solutions, right and left hand, begin to segregate into two different solutions until eventually one dies out and the other one is the one which has in this model a constant concentration as a function of chain length. So this is now the same thing, but in a spatially extended model. So again we see the chain length. Here in our 2004 paper we only went to a chain length of 10, but we have a spatially extended system. So what we should be thinking of is that we do an experiment where we grow the chain in one particular position and the chain becomes longer and longer. And if you wait, then eventually all space, the entire histogram, the vertical direction is really histogram as a function of position, the entire histogram will be filled. But this is only at one particular location where the perturbation initially happened to have a bias towards the left-handed ones. At the same location where the left-handed polymers can grow, the right-handed polymers, here denoted by R, cannot grow, or they decay, and so it shows up as black. Note also that we have a fairly sharp transition between the right-handed polymers here, which end here, and have actually maximum concentration just at this interface, compared to the other location where the left-handed ones grow. Of course, one of the reasons why the concentration is so sharp here at this right at the interface is not really because of the presence of the interface here, but because you have the largest loss towards the growth of along polymers in the middle, and that's the reason why there's a dip here. So the dip is not because there's local maxima for certain reasons, but because the dip is because the chains go quickest if they are far away from the location where the chains would grow into the opposite direction. So if we are thinking of a spatially extended model, what we have done here is we have used the equations, but by replacing the ordinary time derivative by a partial time derivative, this one should have been a partial time derivative, plus a spatial double derivative Laplacian multiplied by some diffusion coefficient. In the previous plot we used the full equation. This is the reduced system already. But in the full equations we also had the similar diffusion terms. Reaction diffusion equations is the general name for these, and such equations have interesting behavior in that they allow typically for the propagation of fronts. So a prototype of a reaction diffusion equation is this is a very simple equation which is called the Fisher equation, which has a single time derivative, a double spatial derivative, and then it has a reaction term which here corresponds to one that can grow exponentially. This, if x is small, forget about this term, we have exponential growth. X dot is equal to lambda times x, the growth rate is lambda. But then the system can also saturate at the value where once x becomes equal to unity, because that shuts off this exponentially growing behavior. So what we have locally is the situation where we have a front. Suppose we have initially such a front, then in those locations where there is still some concentration, the growth will be kind of rapid, but there in those locations which have not been perturbed yet, there will be no growth as yet until the system either grows by stochastic forces locally or until the front has actually reached this position. So this is the term that leads to the growth here, and the diffusion term leads to the spreading of the seeds for prolonged growth at the next location. And so that's the behavior of this Fisher equation. One can calculate that this leads to a propagation of a front, which means that x is a position of is a function of position minus the front speed times time, and this front speed is equal to twice the square root of the growth rate multiplied by the diffusion coefficient. So it's a constant value, which is remarkable. Or rather, what I mean is that the front speed is independent of time. Normally, if you have diffusive behavior, we expect that diffusive waves expand like the square root of t, for example. But in this case, it expands linearly. So one of the applications, of course, is the application to the spread of the Black Death through our medieval times. Here we have seen from records how the Black Death spread from the Mediterranean towards eventually Sweden and all the other countries over the time scale of just a few years. Now, the propagation, of course, is here accomplished by people walking around, which is really spreading the disease.
There was also warfare, though, wasn't it? Which is
yes.
Big thrusts of masses of people with, which
one would think so, yes.
Which is an extra element in the model, maybe.
And then the warfare may have been quenched again by the Black Death. So there's probably a lot of more work that one could be doing here. So that's something for the historians to follow up perhaps, and maybe they've done it already. I know that similar equations are actually used now in archaeology, because you have finds of interesting artifacts. And also there's interesting aspects, of course, because of rivers in such cases, which then hinder, of course, the propagation of people migrating. But that's a different aspect here. So we have this diffusion term, and in this case we have some rough idea how quick the diffusion is. It's certainly not done by any molecules exchanging, but by people exchanging from one place to the other. In this one-dimensional reduced model that I had on the previous view graph, the behavior as a function of time and space would then look like the following. The setup is very similar to the one I showed you in the beginning, where we have again a one-handed perturbation in one location initially. So the background is red, which indicates that the initial state was a racemic one. So it's not a zero state, but it's a racemic one, which is an equilibrium state, but it's an unstable equilibrium. It's just waiting until it's being disturbed. But locally it is disturbed sufficiently strongly by towards the left-handed direction at this point and towards the right-handed direction at this point. As time goes on, this comes to full saturation at around this time for the left-handed one, which is a little bit stronger here, and for the right-handed one a little bit later because it was weaker to start with. So eventually it will reach saturation. That's the time when in one place we would have reached full chirality. So if you are asking the same question, what would happen without diffusion, I would say the system would have been able to reach full homochirality at exactly this point, because it has grown exponentially fast and has reached 100% homochirality at this point. Of course, it does depend on the initial strength. If the strength was a little bit stronger, it would have been a little bit earlier. But then it propagates, like the Fisher equation predicted, with a finite speed into the open racemic areas. So we see from the slope here the speed, which is then exactly equal to twice the square of the local growth rate multiplied by the diffusion constant. However, once these two fronts come into contact, they begin to compete against each other. Before this, they were just running into unspoiled areas. So you had the Black Death migrating into people who are healthy, and they, of course, are inflicting the healthy people. But once you have the Black Death coming into touch with the White Death here in this case, you have two different diseases, both competing for dominance with equal strength. But because both the Black Death and the White Death here have equal strength, there's the impasse, and so that leads to the stopping of this front. And this is a result in one dimension. But it's not generally true. In 2 dimensions and 3 dimensions, this will be somewhat different, and this is seen here by this graph. Here we see the same behavior, just again, reaction-diffusion equation, but now in a 2-dimensional model. What we see here is, again, right-handed on the left, and the other way around here. Well, let's do right-handed on the right and left-handed on the left. Keep things simple, and we see here that there are domains, little rings, and watch out for any of these rings. Let's watch this ring here, and let's see what happens as a function of time. And so as time goes on, they shrink, and now this one shrinks. This is a periodic domain. So how long do we have to wait until the rest shrinks? This depends on simply how big the remaining domain is. And this is kind of difficult to see here because, of course, this one is part of this one. So here's one domain, and then here's another domain. So there's 2 domains left, and we have to wait quite a long time until this all disappears. And unfortunately, this run is too short, so we don't quite see all of that. So therefore, in the next transparency, a longer run, where we eventually see how this domain shrinks, actually see that this has merged with the other one, and eventually it all disappears. It would be good to see actually the same movie backwards, but we actually see that it has been one single domain all along. It was topologically one domain, and we only see it clearly as one domain at the end.
Is there any significance in the fact that the 2 patterns are very similar? They're not quite
Oh yes,
identical.
of course. Yes. So right and left comes Once left is 100%, then right must be 0%, and vice versa. So the two are in anti-phase, so to speak.
Yes.
So what we see then, if we calculate the enantiomeric excess, which is here called eta, globally, we see that the growth is no longer exponential, it's not even linear, but it's actually piecewise linear. Look at this remarkable behavior. Initially it was quite fast, but then as it grows towards 100% chirality, and here it hasn't quite reached it in this plot, it behaves piecewise linearly. Why is this? And it's really quite remarkably piecewise linear here in these intermediate regimes. So if you calculate the derivative of the enantiomeric excess with respect to time, you see really a step function. Constant linear increase of the enantiomeric excess, which then goes in steps. And the steps are equally big. So you go by one unit, by one quantum leap, from one slope to another. So the reason is actually quite simple. And this is shown here. Sarah already explained these equations. So if you take these reduced equations, those come from our 2005 paper here, and you add these equations, you obtain an equation for the symmetric part, which we call S, and of course for the diffusion term, which somehow got deleted here, you simply have the diffusion term operating on the sum of the two after you've summed the two equations. But then there's simply no asymmetric part in this equation. You just have the 1 minus s squared. So the symmetric equation is completely independent of the asymmetric part, which is equal to the difference between right and left. So you can start solving this equation at one location on its own, and of course the solution locally will be that s is equal to 1 or minus 1. Minus 1 of course is unphysical because the concentrations must be positive. So s is equal to 1 is a solution in those locations, or is always a possible solution of these equations. But then the antisymmetric part has a more complicated behavior. It is a mixture of s and a's. But then to keep things simple, we can assume that s is already equal to unity here. Then we have twice minus unity gives 1, so we have 1 minus a squared, approximately here, 1 minus a squared, divided by 1 plus a squared, multiplied by a. And then we have the diffusion operator. So once we calculate the enantiomeric excess as the concentration difference, right minus left, over the entire domain, we have to integrate over the antisymmetric part. By integrating over the diffusion term, nothing happens. Because the diffusion term is just given, del squared is just given by the divergence of a gradient, and the integral over the divergence is just equal to the surface terms. But if you have periodic boundary conditions, the surface term is absent. For certain other boundary conditions, the surface term is also absent. So in general, the diffusion term is not going to upset this analysis very much. So the enantiomeric excess depends entirely on the properties of the chemistry of this local growth term. And so in this case it's equal to this, which is equal then to the contributions of the to this integral. So if you plot this integral locally, we see here that it is basically 0 in both cases, because either the antisymmetric part is equal to plus 1 or it's minus 1 if it's antisymmetric, in which case the numerator is 0. So outside, and this here, this shows a cross section through such a local block, outside the boundary layers, this integral has 0 contributions locally. And so the only contribution to this integral comes from the boundary layer. But right at the boundary layer, there's this a term which shoots us from minus to plus, and then back again. until it's being quenched again by this remaining term. So within the boundary layer A is of course 0, exactly in the middle of the boundary layer A is 0, then this term doesn't give anything, and so we just have the local linear slope here, which we see very sharply here. So now the reason why this why the front comes to a halt in one dimension is because these two contributions are exactly equally big. The one from the left-hand side is just as strong as the one from the opposite side. However, if the system is curved, the inner front is slightly weaker than the outer front. And you can actually relate this to this integral to the difference in the radii, the inner radius minus the outer radius, multiplied by the thickness of the front. And the thickness of the front will be given by the diffusion coefficient, but the thickness of the front enters twice into the system, and so the length of the front squared is proportional to the value of the diffusion coefficient. So therefore, the rate of change of this must be linearly dependent on the diffusion coefficient, and for the dimensional reasons already, must also then be proportional to time. It's exactly as we see here, because it's piecewise linear. However, the more of these fronts we have, the more of such local positions we have. So if you have two rings, the growth rate, if you have two such rings, the growth rate will be twice our quantum unit. If you have three, it will be 3 times that, and so forth. And so as a function of time, of course, we will gradually delete one front and then the other front, the smallest fronts first, until we have in the end only one front left. And that's the reason for the piecewise linear behavior. Do you know how big the difference is between the inner and the outer in terms of... Let me ask the question the other way around. Suppose you have warriors defending the Black Death and the White Death. So in the inner one we have here the Blue Death people, the warriors standing next to each other. Here's one warrior, the next one immediately next to it. And then on the outer front we have the Yellow warriors. So how many more warriors will be on the outer front compared to the inner one? Will it depend on the radius or not?
It's not.
It's not. It does not. Yes. So just think of this other example, which where it's maybe even very hard to believe. You know that the circumference of the Earth is 40,000 kilometers. So now you take a fire hose all around the Earth. So the length of the fire hose must, of course, be 40,000 kilometers long. And now you take all the firemen at the equator are lifting the fire hose by 2 meters. How much longer does the fire hose has to be? If everything altogether is 40,000 kilometers, it's a huge length. So how much longer must it be? How much?
6 meters.
6 meters? Yes, because it's twice pi, but then times 2 meters, right? So it's times 2. So it's 12 meters. So out of 40,000 kilometers, the fire hose just has to be longer by just 12 meters. It's amazing, isn't it? And so that's the reason why this is such an hopeless battle, because the two fronts are almost equally strong. But what is also interesting and important is that this dominance of the outer ones will never become stronger, even though the thing is shrinking all the time. You can see this for the fun of it just one more time, and then here it's very quick. And in the previous one, this one was a short run. So initially we have quite a lot of these rings here, of course. Here's a ring, here already rings disappeared, but here we see several more. They of course correspond to exactly this point, so both are rings here, and they both shrink. And then of course as time goes on, we quickly lose all the amount of rings, and I think this is already a single structure, just one ring, topologically speaking. So this was then the reason for this slow behavior. If you just have diffusion, and we have also learned now that in that case the enantiomer excess must grow linearly, but it must grow only piecewise linearly, so depending on the number of pieces that we have. And so I think that would be something one should be able to see in the lab. So in the remaining few minutes, let me apply this and say a few words about the APED model, which applies to peptides, unlike the Saunders model, which applied to the RNA world. And so in the Poisson et al. Model, it really is different. And again, it hasn't been talked much about it yet. It is assumed that everybody knows it, of course, but nobody has actually really analyzed or explained it much. And so therefore, I would like to spend a few minutes on explaining some aspects of this. I would like to plot things in such a way that the different lines don't cross, and in such a way that left and right are on opposite ends of the graph. So here are the dimers, here are the monomers, here are the activated monomers, L star, and here D and D star. So the important reaction, one of the important, actually all of these reactions are important. If you neglect any single one out of this already rather sparse reaction domain, the thing is no longer working. So these are it's the absolute minimum of reactions that you have to have. You cannot neglect any single one of them. The only thing you can assume is that certain reactions are fast compared to other ones. So one of the reactions that are quite critical here, and that's what is corresponding in some superficial sense to cross-inhibition, but it's not really the same, is the enantiomeric cross-inhibition. So that's the term which turns an LD into a DD. So it's the first position that changes its chirality. And likewise, enantiomeric epimerization on this one, DL goes into L. So ideal conditions have been assumed, the back reaction for simplicity, just in order to to see why the whole thing is actually working at all, has been neglected. These are the activation steps, and they're also important. So one way of seeing what's going on is by just looking at the final balance of things. So let's look first of all at the reactions which have to do with homochiral dimerization. That happens at a certain rate which they call P, whereas if you have heterochiral dimer production, that works at a different rate, and that's important. If the rates are the same, the model would no longer work, and that means that alpha must be different from unity, less than unity. This model does not really have autocatalysis in it, but let's see here. I mean, that was actually one of the reasons which makes the model appealing, because when in the RNA world we know autocatalysis really has to do with the length of the chain, and for short chains it would be almost hopeless to think of any catalytic action. So the only catalytic action that we could expect is if you have an RNA world where each RNA molecule has at least some 300 monomers. And so one can really not easily think of building up, of getting the RNA world started. However, this model doesn't really have this problem because it doesn't have anything like the autocatalysis in the usual sense. And that makes this model so appealing. So what this model has is, first of all, the polymerization step with an activated monomer producing here, in this case, DD. But then this one can split up into a DD again. So later on I will assume simply that these rates are quick, are not the rate limiting factors. So by assuming that H is fast, you really end up with a reaction where D star, activated D, together with the D, it turns into a D plus D. And that actually reveals that there is, in some sense, an autocatalysis, in the sense that the D can act as an autocatalyst for converting the activated Ds into a D. So, as I said, there's no immediate analogous thing to the cross inhibition, but look at this reaction here. So we have the dimerization of a heterochiral dimer at a particular different rate, alpha times P, producing at LD. But then because of epimerization, it can turn into a D and D, and that one can depolymerize again. Later on, I can again assume that these two factors are not the rate limiting factors, and that helps in understanding the mechanism more clearly. But look at this equation again. There is a catalytic step. So it's not a cross-inhibition step, it's actually a catalytic step. And the catalysis is in such a case such that the D acts as a catalyst for changing an activated L into a D. So both steps are actually catalytic in some sense, in this sense.
What about the LD? Cannot split to L and D? The DL and LD.
This one you mean?
Yeah.
No, this one, yeah, that's important. This one can only change into this. The rate at which Raphael and company did not consider, but this rate is very much smaller. So in order to change an LD into an LL, which is what you're asking.
Yeah, but no, this is epimerization, but in the other one, DD is split to DD. And LL is split to LL. But why LD is not cleaving to L plus D?
You can include this reaction too, because it just diminishes the global effect. You can. Yes, I have the complete model where I take into account everything. And you have just competition between the.
So this best case scenario here, and of course there's a minimal net of reactions, just to understand that it actually can possibly work. So unless somebody else is screwing up this by having more complicated reactions that are not taken into account, this at least would be the pathway how it could possibly work. So just to understand, we need to strip away everything which confuses the view here. So by now already I have simplified the model in such a sense, that we no longer have to worry about the dimers if we assume that all those reactions are fast. So mathematically speaking, you can do the same thing, of course, taking the full set of equations. Even that is not the full set, there's more equations than that. But you can assume that these reactions which have to do with dimers are fast. And if they are fast, you can put the time derivative to 0, even though it's paradox. You're not really saying that this is time independent. You're just replacing this equation by this equation where you assumed that the time derivative can be dropped. That's an approximation. You're dropping out the fast oscillations. So you're dropping out something which is rapidly varying in favor of looking for some average behavior. And then you're replacing these time-dependent equations, explicitly time-dependent equations, by these equations. And so now you've reduced the system to 4 ODEs after you've inserted this. And after you've inserted this, you arrive at equations that are simple. These are just these equations. And if you analyze these equations, restructure them in terms of what the underlying reactions actually were, you exactly arrive at this, which is what I've motivated in the previous graph. And again, see, you note that the value of E no longer explicitly enters. It is assumed to be infinite, but how close to infinite it really is doesn't really matter, as long as it's big. So these are then the rate limiting coefficients. But then we can try to understand what that actually implies. And why does this model here produce homochirality? And that's illustrated here on this graph. So instead of doing this in PowerPoint, I just do it on the whiteboard by PowerPoint assisted. Simply do this here. So let's assume then that we have a small enhancement of our L locally here. That this one is slightly bigger than this. If this L is slightly bigger, that means that the rate at which activated Ds turn into Ls is enhanced. So you actually enhance this behavior here. So you're gaining, so after you increase L a little bit, you're already increasing L even more. But that means, of course, that this one must shrink. But if this one shrinks, and because of this minus sign here, that means that this rate is actually even accelerated further, leading to a further drop of the D. And after the D's drop, this supply of D's will be shut off as well, making it even worse, leaving those ones still high. But if this one is still high, the supply from the L's will no longer be strong, and will be shut off as well. And so that keeps this one high as well, at some new equilibrium to be determined. So now at the end we will have these ones both being high, and these ones both being small. And that's the essence of this APED model. So I don't really see anything analogous directly in terms of the Frank model. One is always naively saying that things are just, if they behave like the Frank model, it must be the Frank model. But that's not always the case, as is seen in this case here. So there's, instead what we have is something like autocatalytic behavior in both cases, but the only thing that might possibly correspond to enantiomer cross inhibition is actually productive autocatalytic behavior. So both behaviors are autocatalytic. They're productive. They're producing more stuff, and not like in the Frank model where you have this cross inhibition which just kills everybody, and just the lucky ones that remained are subject to further growth. All right, so this I've now applied to a two-dimensional model. I've shown this already to a few of you a few days ago. It's a very simple setup. This is the initial condition, or close to the initial condition. The time is already t here. So if you calculate the enantiomeric excess, the majority of the domain certainly is right-handed here. And only the minority in the corners here is left-handed. So what's the enantiomeric excess? If this domain is the largest, it must be a positive enantiomeric excess. So start off with an enantiomeric excess of 30% plus, and then let the model run. What would you expect? It goes to plus 100%? Or would you even expect that it goes to minus 100%? I mean, if you start with plus, sure enough, it must end up at plus, right?
That's a good question.
What?
Yes. The answer is there.
The answer, of course, is already there. And I think this is quite beautiful here. So it's quite counterintuitive. But of course, it's completely clear what happens, because I've already explained to you that the inner front is the weakest one. So you just, by construction, you can arrange things such that if a huge, like think of US and Russia, for example. Russia is big, right? And the US is smaller by comparison, but big enough to at least be around the enemy back during the Cold War time, of course. Right? And so as long as the Russians sold Alaska, for example, the Americans can have a full circumference around Russia, even though Russia is extremely big. And then the fight happens really just at each position along the front, of course, and clearly the outer ones will win. And that's the reason why the whole thing shrinks, and as a function of time, of course, here is shown the animation. Sure enough, this ring gradually, slowly, not very quick, becomes smaller and smaller and smaller. Now it's the time 1300 in times where A is unity, so that we're approximately here now, and now it looks like it's going quickly towards the end, but that's happening in such a way that the enantiomeric excess really behaves exactly constant. Now this is a different model. This is really the Poisson et al. Model, and yet the behavior is very similar. And that's you can actually do the analysis in terms of the term that is the chemistry that is pointed out, and the term there looks very similar. It also has a 1 minus a squared times an a term. Right. So to finish off, why did I show? So one of the reasons I showed this is not really because I wanted to explain the cell migration and stuff like this, but I wanted to ask how long would it actually take for right and left-handed life forms to actually develop and possibly even have some remains in the Earth. And so the picture, the forward here is the one from Mike Russell in his American Scientist paper, which was very nice to read. And of course he has a large number of professional literature on this as well, of course. But what he is envisaging is the origin of life in hydrothermal vents. But wherever the origin was, if it was near the surface of the ocean, eventually it may have migrated, and that's what he is thinking of, it might have migrated into the deep biosphere, which is an area that is only now beginning to be studied in great detail, of course. And the deep biosphere would be the only place, if life is there, where it could be protected from opposite life forms. If it was in the ocean, or even in the atmosphere, the mixing time between one position on the Earth and the opposite position on the Earth, Alaska and Finland, for example, which are 12 hours apart, but on different latitudes, so I should rather take New Zealand, I guess, and Finland, or Sweden. They are also perhaps 12 hours apart. Then the time it takes to mix these two places would be no longer than 30 years. So by 30 years they would certainly have mixed, if not quicker. And so there would be no chance really to expect anything like different life forms having possibly survived. Actually, I jumped here over one thing, because what I assumed here is something important. Because if the diffusion really happened with the diffusion constant, it would have taken several Hubble times. That's because the coefficient is that small. The kappa is on the order of 10 to the minus 5 or something. Yeah, 10 to the minus 8, I believe. But that is unrealistic, because the oceans, of course, are in constant motion, and so is the atmosphere, and so is actually the deep biosphere. It's not, you wouldn't really call it turbulent, of course, but in some sense it is actually turbulent if you think of long enough time scales. And so once you have motions here, let me start this movie from the beginning, of course. This is here the behavior on the left, with just diffusion. Things take a very long time, and even then not much has happened. But if you have this kind of situation, it's a mix of right and left locally, and almost zero enantiomeric excess at any given time. But once you wait long enough, there will be so much mixing going on, production of left and right, a lot of new boundary layers are constantly being created, that by the action of this turbulence, you will have substantially enhanced mixing, completely independent of the molecular diffusion. And so in this case, you see the dominance of one over the underhandednesses after a rather short time. By the way, I should say these calculations are done with a code that is being maintained here. This is called the pencil code, which is used for a number of different applications, a lot of fluid dynamics applications. That's why doing turbulence is such a natural thing to do here. The free domain, public domain code where also chemistry is now implemented. So to conclude then, let me say and emphasize that we should really expect domain walls to form. I think that will be very interesting to analyze in chemistry. It is often overlooked. Although, of course, we have the Belousov-Zabotinsky reaction, which actually demonstrates behavior that is related also to domain walls. However, as far as right and left-handedness is concerned, we cannot really expect anything like oscillatory behavior. So such behavior has not been seen so far. If such behavior occurs, it may, of course, be possible, but we have to look further by modifying models, perhaps. Another striking thing is that the enantiomeric excess of the final state can be sometimes very different in sign from the initial state. This is seen by this one experiment where we start with plus 30% and end up with minus. All this business is something which I think is worth checking out in experiments, but as far as astrobiology and the origin of life is concerned, we really have to work with flows all the time, and in such case, much of this very nice analysis unfortunately becomes quite irrelevant, because everything is really just determined by these very short and turbulent mixing time scales, and that's how you end up with 30 years even for the deep ocean. So, thanks.
Thank you very much for this fascinating extension of these models into something, getting more relevant to dimensions. So, questions?
In your Cold War model, Soviet Union surrounded by
Yes.
The reaction time is different. For example, if you increase the order of the reaction term, those territories still classified inside territory, always classified the outside.
You mean if the right-handed one is different from the left-handed one?
No. The reaction terms. Reaction terms are different order, and maybe higher order.
Yeah. So you mean for dimers, different reaction times? Yes. I've actually taken this into account in one calculation that I've not shown here, in a one-dimensional calculation. You would expect that then the fronts, the thickness of the fronts for dimers is different from the reaction front of the monomers. On the other hand, this doesn't actually happen. And the reason for this is because of the chemistry, which very strongly couples, of course, monomers and dimers. So that reaction is very strongly coupled by this, and the diffusion coefficient is rather small and less important. So you don't actually have different fronts, it seems. However, there's perhaps still scope for not giving up on this, even though there's scope, hope, not giving up is a search for perhaps exciting solutions in such a case where the diffusion coefficients are different. Certainly in 2D one should look into that, and this has not been done yet.
This is just a comment, but that suggestion that you might need to make me remember that the phenomenon of chemical diode, there's phenomenon of chemical diode. There are the reaction not only generate oscillation but also chemical waves.
Yes.
And geometrically, two reaction cells are here, and one is flat, and this is equal like this kind of shape. Wave cannot transform from here to here.
Yes.
From here to here.
Yes.
Just the diffusion change.
Yes.
Geometry difference change the diffusion. So that's why one-way chemical wave transformation is possible.
Yes.
And the simulations is very similar to that phenomenon.
Oh, I see. Yeah, right. Interesting. Yeah, we certainly will continue looking into exciting aspects of this. Even though with turbulence, of course, unfortunately, we don't really see the reason for astrobiology, but for the labs, it's interesting. Yeah?
So when you write DL, the dipole time, generally speaking, D is amine terminal. And so in this case, if you use aldehyde like a catalyst for the mineralization, only the D can change in L, and never L can change in D.
Yes, right. That's
right.
Yeah.
If you use such catalyst.
Yeah, so I think what you're saying is that this step does not happen, and only the other one happens.
Yes.
That's right.
And D cannot change. D cannot change in L. Only L can change in D. In this case. Yes, L can change in D.
If this is the N-terminal position, yeah.
If the amino group is outside, is on the left.
Yes, right.
And if the catalyst is amino group, aldehyde.
Yes. Yeah, that's an important aspect. That is what causes the asymmetry in the reactions. So it's not a asymmetry as such that the equations for left and right are different, but it's an important asymmetry as far as the beginning and the end of the chain is concerned, and that's at the heart of this mechanism. I think that's what you're saying, right? Is it?
I was over and comment in the Frank publication, it was already commented on the French. It is about the convexity, and that in the simulation it was possible to see all this. It was already proposed that it would move no way. But what the hope to do it simply by pencil and not by foot.
Yes. So
I suppose that is in material science, because that is a common phenomenon. Because for other people coming from other fields, it is difficult to imagine that things works in this way, but it is proposed so simply.
Yeah, right. Yes, I remember also when I read this paper, there were a lot of insight was in that paper. There was also a discussion about the different behavior if the origin of life is a frequent phenomenon or not less frequent phenomenon. That was another aspect that I think was discussed in the paper by Frank. It's a very interesting paper, so I should
and then the
Read over again.
turbulence, the effect of the turbulence,
Yes.
chemically, because that is the methodology of steering, the reaction of
Yeah.
But,
Yes.
in these models, you speak always about the diffusion. And
Not always.
you don't modelize with scattering in addition.
Oh yeah. What scattering mean in terms of fluid model here?
You will avoid going in a fixed direction, because when the scattering is often the dispersion, it will be more directional. Do you think it will have some influence in the structure?
Yeah, I'm still
Evolution,
can't quite imagine how.
Of diffusion of the scattering is influenced.
So is scattering something like a backwards transfer? So something from small scales to larger scales, perhaps.
Yeah, imagine the electron transport in a conductor.
Which is non-local, perhaps.
For
Yeah.
instance, you have, as it could be, the stone arrive.
Yeah.
Due to the scattering, some parts of,
Mm-hmm.
then you have
Uh-huh.
the STOL that have not the possibility to arrive to the other end of the recipient.
Yes.
There is the scattering.
What I'm not quite sure yet, but it sounds a little bit like this would also enhance the speed of mixing. And once you enhance the speed of mixing, you're producing more frequently these boundary layers. By producing more quickly boundary layers, the time for the war to finish is getting shorter and shorter, because you have war on so many different fronts. You're exhausting all your tanks, of course, very quickly.
I think, if I do it correctly, your model is also correct for coalescence of clusters into dimensions. Because in principle, one can investigate the coalescence clusters by Brewster angle microscopy or by X-ray gradient diffraction. And in principle, if you're taking, let's say, you're taking two enantiomeric clusters, separate clusters which are depositing on the water surface, for example, and you're measuring the coalescence of them. Maybe you can level one with a fluorescent dye or something like that. It should be something very, very similar.
Yeah, right.
Because the activity
If
is only one element into your system.
Yeah, so the picture I would have then is that you have clusters of obsolete-handedness which are very quickly brought in close contact with each other.
Yeah.
And that would enhance, of course, the loss of one towards the other one, enhancing.
Now, when you're speaking about can be checked by experiments, in principle, you must not introduce the problem of their activity, but just the problem of the mixing.
Yeah, you see. So I think basically what you're asking is whether all of this is actually also true for crystal growth. And I think I'm fairly confident so, but unlike with the APED model, I have not actually looked at the nature of this term. But I would not be surprised if we again have such a term then underneath the integral. So if we had in 2 or 3 dimensions such a term underneath the integral, A means the asymmetric part,
another part,
it would be the same behavior. That needs to be checked
another
first.
part is you cannot.
Can you overlook this? Do you know whether that's the case? You go.
I think the denominator.
Yes. Copy different. Yeah. But then this one is the same.
So the numerator is the important part, and that just corresponds to the initial.
And that's the same, yeah? So that, in other words, and I'm not surprised, even for the crystallization model, the chemistry term or the nonlinear, the growth term, not the non-diffusion term, behaves still like this here, and would therefore have the same behavior. And that means, yes, the answer is yes, we can therefore check the whole thing holds with crystals, and we would expect such behavior. And I think it would be interesting to, but if you do grinding, of course, you immediately begin to mix.
We're not thinking about grinding. I think in this conference, grinding was the central part. Without grinding.
Yeah, right.
But also, in what sense, you introduced, let's say, the Jonathan equation for having departure from the binomiality as introduced? In what sense the two models differ from one another?
Oh, Jonathan's model, yeah?
No, because
For crystal
in
balls.
model, no, for the polymerization that you introduced of the reading measurement experiment, you introduce some kind of departure from the binomial state, right? And you also have to introduce something departure from the binomial state. You're saying the L is up. In what sense the two models, the elements of the two models speak to each other? Did I express myself well?
Yeah, more or less. But then should then maybe really write it down in terms of equations. And I see that Jonathan's already taken pen and paper here. So maybe that has to wait until he has. But does Jonathan have an answer to this?
Your alpha term is the difference between the binomial. Alpha is 1 and you have the binomial distribution. You've got P and alpha P.
Yes.
If alpha is 1, you have the binomial distribution. Alpha is
Oh, because that will be a disaster then. Because if alpha is equal to 1, the whole thing doesn't work, right? So it's and that's exciting, of course, because when you do all this homocorrelation stuff, then eventually, as our chairman told me already, everything looks completely trivial at the end of the day. It always works, basically, you're saying, right? And now we have quite easily, actually, cases when it doesn't work. And I think that's when it's becoming interesting.
Yeah, the fact that alpha is less than 1 automatically means you're in a non-binomial case where the homopolymers are over-expressed except for non-distribution, and the heteropolymers are under-expressed. So that's necessarily the same condition in non-quantification.
It's amazing. So it's not always trivial, even though there are so many people who can make it work at the end of the day, but it does not always work. It's just the good cases that people show, of course.
Any more questions? Axel asked me if I would, at the end, would somehow summarize the meeting. I said to him, I'm just not competent to comment and summarize on so many things, because of all the technicalities involved, the synthesis, the analytical. But